Okay. So let's jump in. Again, most of the code lives in the package directory, and for us, we need to go to the app directory, master, commands, and build. And the handler code is in handler.go. So every time the on command function is called, we have the parameters, we know what we want to do, and now there's a lot of parameters. And now we go through the build command steps, and it, if you look at the different phases, it has three major phases. First, we do static analysis, kind of like X-ray light. We do static analysis on the target container image. And then we do dynamic analysis, similar to what happens with the profile command. And then once we're done, we process the results, and then we build an optimized image. There's a couple of other things that happen, and we'll get to it. So when we, how's the screen share? Can you see the code?
Yes, I can see the code very clearly. Very clear.
I'll make it a little bigger. Okay, so when we start the command handler, the first thing we'll do, we'll create a command report. So every time you run a command, there's also a command report that we populate with different pieces of information. Each command has different bits of information, and
is this what it goes into the slim.json file?
Yep, exactly. So most of the information in the command report is also printed to the console. So this is the purpose of the command report file, is to provide a machine readable output that you can process. Okay, so we create a command report object, and then we create a Docker client so we can talk to the target container, so we can get the target container information. There's also an extra step here in the build command. You can, most of the time you point DockerSlim at an existing image, but with the build command you can also say, you know what, we don't have a container image yet, but we have a Docker file. So you can point to a Docker file and it will build a container image first, and then it'll optimize it. So that happens because there's a common pattern. A lot of users would use Docker build to build their image, and then they would use DockerSlim build to optimize that image. So this allows you to have just one command, and it would build from source, and it would optimize. And that's what we do here. We check to see if the dial parameter is specified, and if it's the case, then we build an image first. And right now it's just doing a basic Docker image build. There's nothing special about it. It's very similar to using the CLI.
That was my next question. Is there any advantage in using this to build the container as opposed to build the image, as opposed to using the default or the normal Docker build? Do you get anything, or this is just calling Docker build under the hood?
There's no functional advantage. The main difference there is that you don't need to have two separate commands, but behind the scene it uses the build API call, which the Docker build command uses as well. So it's doing the same thing behind the scene.
Okay.
And that's what we do here with builder, new basic image builder. So it's not building an optimized image; it's building the standard image, and then we just check to see if there are any failures, and then when we are done building, then we also point the target ref variable to the image that we just created. And the rest is the same. Then we do a few extra checks related to, for example, we check to see if the network that was passed is valid, so we can connect to it. And then we start the static image analysis phase when we create the image new inspector. This is a container image inspector, and it collects basic metadata about the image. It's not the full X-ray capabilities. It's just basic information that we care about. And the number one goal there is to get the basic information about, well, first, verify that the image exists. And this is one thing that we do here. We check to see if the image is actually there. And if it's not there, we fail. The second thing is to get a few other pieces of basic information about the image. And the third one is to reverse engineer the original Docker file. So when you run the build command, you also get the reverse engineered Docker file. Let's see. So here, do you want to go inside of the inspect phase?
Yes.
Okay.
If you already have the Docker file, if you're building, is there like any advantage to that because you already have the Docker file? There's really no reason to use the reverse engineered Docker file.
Very true. So the reason it's there is because there's a number of steps that it goes through, and potentially you can have a condition to check to see if you build it from source. If you build it from source, you already have the Docker file, so you don't need to reverse engineer the original Docker file because you already have it. So you don't really need to do it. So in the inspect method, we get the information about the image from the local Docker installation. And then we reverse engineer the Docker file, and then we save it. And if there is a reverse engineered Docker file, we collect additional information, and we save it in the command report. We save the image stack information, and the image stack information is the information about the images you have in the target container image. For example, you build your application image, but it's built on top of a base image. So the image stack will have the information about your application image, and then it will have the information about the base image.
Okay.
So you know about the composition of your Docker image.
Is this provided? Is that from the inspect or similar to what you'd get from X-ray?
Yes, yeah, but you get a lot more with X-ray. That's why I called
Okay.
it X-ray Lite.
Okay. Okay.
Yeah. So the next step is to do dynamic analysis. To do dynamic analysis, you need to create a container inspector instance, and that's exactly what we're doing. There's a lot of parameters here, and we'll step into this called we set up an object with a lot of those past parameters, and then we also figure out what we want to have for the entry point. So it's possible for you to override the entry point and the command instructions when you run DockerSlim build, and that's what happens here. We save the original command information, and then we return for the most part. Let's see. So we created a container inspector, and then we run the inspector. And then when we call the run container method, first thing we do, we start figuring out where we have the sensor binary. So that's what this code is doing. It builds the full path to the sensor executable. And then it ensures that the sensor executable is there. And if it's not there, we fail.
I'm seeing that there is an extra check to see if this is on a MacBook. Is there like a specific reason why this doesn't work on maybe Mac OS or any other specific OS?
So with Macs, you don't have Docker running natively. You have it running through this virtual machine or through this special setup, and because of that, you don't always have access to all of your file system. So not all local directories are shared with the Docker VM. So depending on where you have the executable, it may or may not be usable. But there are, so there are a few macOS checks there.
And is there a chance of that failing if someone is on macOS?
Yes,
Okay.
there is, and in some cases,
Okay.
It has failed in the past. Then the next thing we do, once we locate the sensor executable, the next thing we do, we set up the volume binds for the target container that we'll create, and we'll set up the binds for the volumes you pass to the command, and we also set up a volume bind for the sensor if it's configured to do that. So originally, DockerSlim would always mount a local directory with the sensor to the target container. And that worked fine for local executions, but it doesn't always work for containerized executions, for example, in Circle CI or GitLab CI or anywhere where you run DockerSlim in a container, because it's not always possible to mount local files from a container to another container. And because of that, the original mode to mount a local file is still there, but it's turned off. And what we do, we use a volume to mount the sensor. So now there's an extra step before you mount. To mount the sensor, first you create a volume, and then you copy the sensor there, and then you mount that volume into the target container. And this is what happens here with the ensure sensor volume call. Here we create the volume. If it doesn't exist, then the call create volume with data points to the local sensor path, and then what it does there, it copies that sensor executable to the value.
And just for our audience's sake, do you mind explaining what the sensor does?
Yes. So when you run the build command, and once you're done with the static analysis for the target image, you go to the dynamic analysis phase. The dynamic analysis phase requires us to monitor what's going on with the target container. There are different ways to do it. Okay, I think we lost.
Yeah, you just disappeared.
Okay, I guess that's my internet connection. Okay.
Yeah.
All right, I'll share my screen again. Okay, so when
I can see your screen.
Okay, great. So before we start the dynamic analysis, we need the sensor in the container. Like I said, there are different ways to do dynamic analysis. You can do it with something that lives outside of your container, or you can do it with something that's inside of your target contains. What DockerSlim does, it has a sensor executable. Just it's an app that gets included in the target image before the temporary container is created, and this app is responsible for observing what's going on within that container, and that app is the entry point to the container that gets created. So when that temporary container is created, the sensor executable runs, and then it's responsible for starting the of the container logic. So it calls the original entry point in the container image from the original container image, and then it's also responsible for the IPC with the main process. So it listens for commands to execute, It sends the results back and all of that. That's why that's why we mount the sensor into the newly created image, and that's why we create a volume to mount that image as well. So it's there, and we can call it when the container starts executing. And we'll go through the steps that will explain the details. Okay. We set up the rest of the volumes that we need. And here, if you set the debug flag with the debug global flag for DockerSlim, we also end up passing this -d parameter to the sensor. So it knows that it should turn on verbose debugging in its output. We set up the rest of the container parameters, and here we're setting up the host config parameters for the container. Then we create the container options object with a few configs, the host config parameters, and the base configs. And right there, the entry point field points to our sensor binary path. So when the container is running, it won't execute the original entry point. Instead, it will execute the sensor first, and then the sensor will be responsible for executing the original entry point. Then we override a few extra parameters in the create container options object. Including the user information. If you want to run as a different user, you'll be able to do that. So the next step is responsible for setting up the IPC channels. So there's a couple of channels we have. There's one channel to send commands and return replies for those commands, and another channel is to provide events from the target container. And to make sure that it's possible to connect to those ports, we override some of the container create parameters to make sure that those ports are. I can't click on that, but there's a couple of standard ports that we use for the command and event channels.
So just for clarification, when we're doing the HTTP probe or any exec, it's basically after the entry point has been run using the sensor step, right? Okay.
Yep. Yeah. And when the probe runs, and we'll get to it, we'll take a look at the details. the probe runs against all exposed ports except for the IPC ports. So those ports will be excluded. And we override more parameters. And we finally create the container based on those container options. And for the containers to know if the container is still running or if it stopped. We also listen for signals. We start the container, and then we get container metadata once it's started to make sure that it's running. Now we got to the part where we expect the target container to be up and running, and we set up the IPC channels. And there's not a lot of interesting magic going on in the IPC channel. Well, both of those channels. But yeah, it just sets up a couple of structures so you can talk to the target container, to the sensor in the target container. Okay, so back to, okay. Now that's where we send the first command to the sensor. So we create a start monitor command, and we pass the original container entry point information. And that container CMD includes all of the entry point and commanders. So we grab the first element from that slice and we set the app name to it, and the rest of them will be passed as app arguments. And it's done so we can use the standard system command API library in Go, because you need to specify your application name as one of the parameters, and then optionally you can pass arguments to it. Then with this start command, we add a few extra parameters. For example, if you use any of the include flags, for example, if you want to include an extra directory in the optimized image, that information gets passed in the start monitor command as well. The includes, the excludes, and other metadata that the sensor needs.
Let me ask Kyle, for containers that need, or images that need build arguments, how do we pass that when we use this build command? An example would be, let's say I want to use the GitHub sharp as version for the container. So I pass it as a build argument into the container. So the container, or in Go, when you need to pull in private dependencies, you might need to set the GitHub token inside the container so that you're able to build the Go binary by pulling in private packages in private repos. So how do we go about that?
So this is handled separately. So right now we're dealing with the dynamic analysis phase, and the builds, they happen before or after. So when we hit the initial, so if you point to a Docker file, before you get to Docker analysis, you build your fat image and all of that information that you mentioned, the build args, and all get passed to that phase. And there are a number of build flags for that. Most of them, they're prefixed with CBO, container build option. So that that information gets passed. Most of the standard Docker build flags, you should be able to pass those, at least the most common ones. And
okay.
with the optimized image, again, this happens later on, where we collect the artifacts from the temporary container image, and then we copy them, and then we start the optimized image build process. So, whatever custom build options we might need, they would go there. We wouldn't pass them here because we don't do any image building in this phase. We're collecting information and we're collecting artifacts. That's all. So if you need anything from the good image, you would pass instructions about that. For example, the includes. You want a specific file to be included in the optimized image. It would end up in the includes section, and the sensor will then copy that file you wanted, or that directory you wanted back. Yeah, so the build flags and all of that, that's handled separately in a different phase, and we wouldn't pass them here. And then, so we can also use a different user to run the target application in the container. And then once we're done building the start monitor command, we send it to the sensor. And then we start listening for events from the temporary container, from the sensor in the temporary container. So we have this loop. And the main purpose for this loop, we're waiting for the sensor to tell us that it's done initializing, and the done event does that. When the main application receives monitor done event, it means that it can go to the next phase. So let's back to the beginning. Run container. Run container. So we started the container, the temporary container, the sensor in that container, the DockerSlim sensor is running, and it also this also started the original application in the container, and now the original application is running, and we're ready for the next step. And the next step, with the next step, we figure out how we want to transition to the next phase of processing. And here we look at the continue after mode for the build command. So the continue after mode is used to indicate when the build command is ready to start the analysis phase, the post-processing phase. It's used to indicate when the target application is done and the sensor is done, and it's time to collect the results and analyze those results. There are several continue after modes. The most basic one is enter. So you just press enter on your keyboard, and that way the build command knows that we're done monitoring the application and collecting the information we need, and it's ready to move on. Sending a signal is another continue after mode option, and running the HTTP probe is another one. And there's also a timeout option where you can wait, 2 minutes, 3 minutes, and then continue to the next phase. So the most interesting continue after mode option is the HTTP probe. So when you have that continue after mode option enabled, the build command will wait until the HTTP probes are done, and then once they're all done, it will move on to the next phase. So here we check to see if the HTTP probe continue after mode is enabled, and if it's enabled, we create a custom probe object. And then we set up a channel to signal when the probe is done. So the probe object has this done channel, and we copy this done channel to the continue channel in the continue after object, and then we're going to wait on it. And you can actually combine multiple continue after modes. You can combine probe and exec. And exec is one of the other modes where you specify a shell command or a file with a bunch of shell commands that get executed, similar to how things are executed when you run the docker exec command. So it's just a convenient way to run those shell commands out of band. And that's what happens here. You have more than one continue after mode, you're going to have those n%. Symbols, and so we have a loop there. We'll loop through all of those modes. Not all combinations are supported, but you can definitely combine the exec and probe modes together, and some of the other modes might work as well. So here, for example, for the signal continue after mode, we listen. We'll listen for a signal, and once we get it, once we get user one, we'll continue. Yeah, with the timeout, we just wait for whatever time was specified. And the HTTP probe mode, we're waiting. We're waiting until the HTTP probe executions are done. So once we're done waiting for the HTTP probe to finish, and that's usually the continue after mode you end up with. When you point to a container image that has exposed ports, it will the build command will default to the HTTP probe continue after mode, and then it'll run its probes, and then we'll end up here by default. So when the probes are done, we need to tell the sensor that it should stop collecting the information, and for that we use the stop monitor command. And we send another command after that. We send the shutdown sensor command. So at this point, we should have, and when we send the stop monitor and the shutdown sensor commands, once all of that is done, the main application will get a couple of files and a bunch of a couple of generated files. The first one, the reverse engineered Docker file, that's one, and then from the sensor we'll end up with the container report JSON file. That will include a lot of metadata about what happened in the container. And then there'll be a files.tar file with the artifacts that were copied from the target container. And then after we're done shutting down the sensor, we shut down the temporary container. We check to see if we have data from the temporary container, the container report, and the artifacts. If not, we fail, and then we process the data. We don't do a lot here for now. We do two things. We generate an app armor profile, and we generate a sec profile based on the information we have in the container report JSON file. And then we get to the final phase where we create an optimized image. So we create a new image builder. And there's a number of parameters here we end up with. So when you create an optimized image, in addition to copying the collected artifacts, you can also change some of the instructions and configurations in the optimized image. For example, you can remove volumes in the optimized image, or remove environmental variables, so you can edit other metadata. You can add labels, remove labels, and all of that. Then we run the builder, and we execute an image inspector on the optimized image just to make sure that it's there. And so we can also collect additional metadata about the created image. And we save some of that metadata about the optimized image in the command report. Then we save more information, and we print most of that information out to the console. And right there, you can see that we're not printing directly, but we're using the execution context for that. And when DockerSlim is executing in the CLI mode, that information gets printed to the screen. And when it will get executed in the server mode, which is not there yet, that information will be sent back as HTTP response data to the other side. Then we save the command report and optionally copy the metadata artifacts like the seccomp profile to the target location. And then we also archive the state data. And this is necessary for the containerized executions when you don't have access to the container where DockerSlim is running. So that way the results are saved into a volume, and then you access that volume to get the results. And then we save the report. I would say that's pretty much it there. And the next step is to take a look at what happens when we run the probe.
Mm-hmm. Mm-hmm. The process is still the same even if you have the multi-stage build Docker file, right?
Yep.
Okay. And is there no. Oh, okay. You answered the question while you were talking, so that's fine.
We can take a look at the probe. And the probe code is located in a subdirectory in the container inspector. Originally, it was HTTP only, HTTP1 only, and then it expanded to HTTP2 and then WebSockets and all of that. So we actually need to refactor that. So it's not limited to this context, because there's a placeholder for a probe command where you should be able to execute the probe on its own. Plus, we also need to have other types of probes, so it's not just HTTP. For example, gRPC, even though it's on top of HTTP2, but the goal there is that, now that the original probing capability has been extended beyond basic HTTP probes, it makes sense. Make it more generic and find a new place for that package. But anyways, so when we create a new probe, we save the parameters we got passed, and when you run the build command and the profile command, you can specify a whole bunch of different parameters, HTTP probe parameters, and they're super useful for a lot of different use cases. But there's a couple of interesting parameters, new and interesting parameters that still need a lot more work. The API spec parameters is one of those. Well, a couple of those parameters, actually. It's pretty interesting because you can drive the probe based on the Swagger spec you might have, either from a file or from an endpoint. So by default, the HTTP it finds all. It looks at all exposed ports, and then it sends a simple GET request on those exposed ports. And that's pretty much it. You can specify custom commands to specify custom paths or parameters for those HTTP calls. By default, it's a simple GET / call. And if you specify an API spec, then the HTTP probe will go through the spec definition. It'll identify the endpoints there, and it'll make calls to those endpoints. And the crawl parameters, they're useful if you want to customize what happens when the crawler is running. By default, the probe will also execute a crawler, and if you have a web endpoint, that means it'll look at the response data, and it'll extract all links that it discovers, and then it'll make calls to those links, and then it'll keep doing that until it's done crawling everything, unless you limit how many calls you want to make or how far you want to go and all of that.
About the API spec files, so a lot of microservices don't, or at least a lot of services that we package in containers don't work in isolation. They kind of need a dependency. What happens in scenarios where you maybe need a database to be ready fast before doing a HTTP or making a GET call, or you need a different service to start up before you can make a GET call to that service or a post or whatever. What happens in those scenarios?
So that's on you right now, and it's expected that all of those dependencies are already running. And when we looked at the build command initialization, one of the things that happened there is that network parameter check. So that's related to that kind of expectation. You're expected to have all of those components up and running, and you're expected to specify the network to use to connect to those components. Pretty soon, there'll be a way to specify a compose file so DockerSlim can start those dependencies for you, so you don't have to do it manually. It'll do it for you, and then you won't have to have a separate setup. You won't have to specify the network parameter. So there'll be less work. But for now, you're expected to have all those dependencies running, and you're expected to configure extra parameters for the build command in order to do those dependencies.
Okay, that makes sense. Sounds cool. Can't wait to get to a point where you can just have the Docker Compose file as a custom flag, and
Yep.
we're able to start the containers in the back. And during
Mhm.
this temporary container stage, we can be able to connect to them and do the props as well.
Yep.
Yeah.
So the custom commands, you specify for the build command, they end up in this command, field, and then another relatively new parameter, API specs, is a recent addition, but the latest addition is this probe apps parameter, and it makes it possible for you to run external applications when the HTTP probe is running. So you can say, hey, I want to execute curl when I'm running, when the HTTP probes are executing. So you can specify custom flags for that, and then those applications will be executed. And they're local to the environment where you run the main application. So it's a nice way to extend the probing capabilities, and also it's a nice way to integrate with the flow, with the execution flow. So if you want custom logic executed during the HTTP probing phase, you would leverage the probe apps for that. So let's see what happens when we execute the probe. And like I said, what we do, we go through all available ports, expose ports, and then we try to interact with them. But we do skip the IPC ports, and that's what happens here. We skip the command port and the event port. So we end up with a subset of all ports stored in the available host ports structure. And then, depending on the parameters that you might end up with a subset, because your container image might expose 10 ports, but you pass a flag saying that, you know what, I want to probe only a single port, and then that, the target port flag makes it possible. So we go through the target ports, and then we check to see if the target ports match the ports that we know about, and then we save only those ports. Yeah, and then we update the available host ports structure and remove the ports that were not targeted. So if there were any explicitly targeted ports, we removed everything else that wasn't explicitly targeted. And that's what this delete call does. And after all of that, we end up with the final list of ports that we want to probe. And we save it in this ports probe structure. And if there are any API spec files, we'll load those. When the probe runs, when the start method is executed. We have this go routine that we use to execute the probes. So let's see what happens at the end. Yeah, this code needs to be refactored because it's a lot of code. It was pretty small originally, but then it grew bigger and bigger. Yeah, so the start method starts this go routine that executes the probes asynchronously, and then it signals when it's done using the done channel. So let's see what happens when we execute the probes. We print the information about the ports we're probing and the probes that we're sending, and then we go through the ports we want to probe, and we make the calls against the ports. So we go through all of those commands that we have, and the default probe command ends up as one of the commands. So at the very least, you have one command in this collection, in this CMD's collection, and it's get /. And depending on how the command is structured, it's possible to specify a custom request body. It either comes from the command file where you specify the commands, or it's passed in line. But the body can also be loaded from a separate file. So it's possible to have more than one custom commands in a file. And then for each command, it's also possible to have a separate payload file. And that's what happens here. If there's a separate payload file, we load the data in the request body. And then for each protocol that we want to probe, and that's usually HTTP or HTTPS, but depending on the command, it might be, if you have a custom command that says, I want to send a WebSocket probe, then the WebSocket protocol will be there as well. We set up a few call parameters for the probe command. And here, for example, if the probe command is a WebSocket command, then we create a WebSocket client. And I'll skip the WebSocket call there. So if it's not a WebSocket command, then we end up with a standard HTTP client, and then we have a loop based on the maximum retry count, and by default I think it's 5 or 3, one of those. And we make an HTTP call there, get the results back. If it was successful, we get out. And then we also have a way to probe endpoints based on the API specs. Yeah, right now the logic is not fully decoupled, but the HTTP probes and the probes executed based on the API spec information. So here, what we do, when we get the first successful HTTP probe execution, we use this as an opportunity to run the extra probes we generate based on the API spec. That's why there's this check. If it's the first time we get an OK response, then we'll run those. We'll try to run those API spec-based probes. And it's set up that way to make sure that we don't try to run those API spec-based probes before the target is ready. So we want to make sure that we run them when the target application is available. And that's why we also initiate the crawler here as well. So we have an HTTP probe command that was successful. That means that the target is available, and for each HTTP probe command, there's a flag to indicate whether or not you want to start a crawler based on that command. And by default, it's enabled, but you can disable it. So let's say that we had only a single command, and that was the default command, which is get /. And then by default, the crawler would be enabled, and then it would start the crawler there. It would make another request to the same endpoint, and then the crawler would read the body, extract the links, etc., and do its magic. And if it was a successful request, that means we don't need to go through this for loop anymore. So we break ice, we keep track of the errors, and we try again. And then once we're done with the HTTP probe commands, we start executing the probe apps. And here we just go through the list of all of those apps, and it can be direct commands like curl something, or it can be a shell command or anything that can be invoked locally. Let's see. And then once all of it is done, oh yeah, one more thing. So if we make all of those HTTP probe command calls and all of them fail, by default, the build command execution fails, because at least one command by default should produce a successful response. If none of the commands produced a successful response, there's probably something wrong with the target. And the best thing most of the time is to fail the execution right there, so there's no misunderstanding about the results. But you can disable that behavior. So if if there were no successful calls and the default behavior is not disabled, we'll exit. But you can potentially disable that behavior using the setting the probe exit on failure to false, and then it will continue working. And then once we're all done, we close done channel, which is a standard way in Go to indicate that we're done. And the main logic in the build command will wake up and it will continue the execution. And that's pretty much it. We can take a look at the crawler code. And there's not a lot of magic there. It's using the CLI, the Go CLI package to do the crawling, so it's not custom, but from scratch at least. So right there, it creates a CLI collector, and it sets up a number of handlers. For example, an href link handler for regular links, and then other types of links, script links, for example. The default HTTP probing behavior will need to be expanded a little bit with an ability. There'll be a new parameter to execute a headless browser to probe the target. Mostly because for some applications you need to run the JavaScript in order to interact with the target properly. And with the with this scroller, it's not possible. You're just extracting the links, and that's pretty much it. But the headless browser will be execute the JavaScript and then interact based on the dynamic state changes in the browser. But right now, it's not there yet. Any questions about the HTTP probe flow? Oh, one more thing before we wrap up. So what are those commands? So let's take a look. Let's take a look at the custom probe structure and the HTTP probe command structure definition. So here you can specify a whole bunch of different fields. And like I said, by default, when HTTP probing is enabled and you don't specify any custom probes, you end up with an HTTP probe command that has methods set to get and resource set to forward. But you can specify custom commands. So there's, for example, using the HTTP probe CMD flag or HTTP probe CMD file flag. And here's an example. Let's say you have a bunch of different custom commands you want to specify, and you want to use the HTTP probe CMD file parameter. Then you'll have a JSON file that might look something like this. So you can say, hey, I have a custom command with the resource set to this custom path. Or you want to use a custom method. So you don't want to default to the get method. You want to use a different method. So you can explicitly specify the method there. Or you want to use a specific protocol, because if you don't specify a specific protocol, the probe will try all available protocols. And then you can add more custom parameters. And here, the last example shows how you can use a custom payload file. So there you can load the payload from a separate file. And you can also specify headers. And if you need to authenticate to the target, it's also possible. There's the username and password parameters. And in some cases, for the API-based, API token-based authentication, you would create a custom header for that. And yeah, and then you would pass the API key through a header.
That's pretty similar to what a Swagger file would look like, right?
Swagger files, they have, they're structured in a way where you have a collection of resources, where the top level key there is the path, and then under that path you have different methods. For example, first you have this path, and then you have a get method section, and then you might have a put method section, etc. It's similar. It's structured in a slightly different way. And with Swagger, you have the resources section, and then you have the parameters section, and then you'll also have the objects definition section and all of that. But yes, you extract pretty much the same, almost the same information. The main gap in the current API spec handling logic is the parameters. The HTTP probe code right now doesn't try to generate request parameters, and because of that, some of the calls will not result in the behavior you might need. And in most cases, it's enough just to get to the endpoint. In most cases, just to get to the handler, and you don't care about the parameters most of the time. Because if you have a Python app or a Ruby app, it does lazy loading, and care about is getting to that file handler, HTTP handler file that loads the dependencies. And that's it. And in some cases, a tiny fraction of the application, there you might need request parameters that look close to valid, but it's a tiny fraction of the applications.
Okay, makes sense.
Cool. So this time we looked at the build command details. We looked at the different phases of the execution. The first phase is this basic. Well, actually, if you point the build command at a Docker file, the first phase is a build phase for the fed image, and then the second phase is the basic phase where you do basic static analysis on the target image. The next phase is dynamic analysis on on the target image where we create a temporary container. We insert the DockerSlim sensor there, and it's responsible for communicating with the main app, and it's responsible for driving the regional app in the container and collecting the artifacts and the metadata it needs. And then the last phase is taking the static and dynamic analysis results and creating an optimized container image based on that.
Yeah, sounds very comprehensive.
All right, so let's wrap things up, and we'll do another session for something else next time.
All right, is there a feature where all these commands are combined? So maybe like build, X-ray, and lint. So it's just like one command. I don't know. We can call it slim, and then it just calls everything in the right, to make it easy.
So there's a couple of things that need to happen. One, the code needs to be refactored to leverage common code better. So it's not, so right now there's a lot of code duplication. So that's number one, refactor to avoid code duplication. So you can reuse the same piece of code that's executed in the X-ray command, in the profile command, and the build command. Step number two is to add extra flags to expand the logic. For example, let's say you run the build command, but you want full X-ray analysis. So you would be able to specify a flag saying that I want full X-ray analysis, not just X-ray light. And then, the same way you might do something similar with the lint command logic, where you want to produce additional report data about the original fat image, so you know about the problems there, and then have an extra flag to indicate that you, in addition to full X-ray analysis, static analysis, I also want to do structural validation on the original container image using the lint checks. And then a couple of extra flags will be helpful to do the same on the optimized image. So let's say we generate this optimized image, and then you want to know more about that optimized. So there'll be a way to say, also run X-ray on the optimized image, and then also run the structural validation checks on that optimized image, so you can compare before and after. So you can compare the results for your original image and the optimized image.
Okay. Looking forward to that. Thank you so much for taking the time, Kyle, to sit with me. I'm looking forward to the next session.
Awesome. All right, let's wrap things up, and let's set up another session.
All right, thank you.